yeah, I have like a space site at the ICC with a few other
I mean, I feel like as long as you're putting in every day and you're doing
Are you also
the
one
best
of
you
the
can, like,
interns?
your time, so you don't know how long it's actually going to take that you're doing it.
How are you enjoying it?
Especially grad students and postdocs and stuff, yeah, it's like, they know how long it takes to do something, and they forget how long it takes on it.
So it's a lot of
And there's big companies like,
looking for data so that I
we try to go to all of them. Me too. So to be like, I know it's hard, but I'll like do
which is something that I
feel like you could. I'm trying to do like more balance. But even though they happen, everybody's using this anecdote.
We went at night,
so all like the city lights
Yeah.
It was expensive.
Yeah.
Yeah, but I think it was worth it. I think it was worth it. Especially
I mean, we stayed there for a while because I don't think they give you like a time. You can just stay as long as you want.
like you have to have
I was like staying around the suburbs.
We like went inside, we like sat down in the rotating area, like you sat on it.
yeah.
I don't know if you're supposed to do that, but we did.
I think it's fine.
It's yeah, I'm sure New York is like this Boston, but much better. There's much more going on.
Yeah.
Yeah. So
That's literally.
Boston's definitely, it's definitely quieter. There's like less activities and things like this. But
No, that's literally my Instagram post.
Oh my god.
It's beautiful.
yeah, I think there's a good chance. There's a good chance.
No,
I'll
what's your
like,
Instagram?
PhD or like law school. I think like ultimately I'll probably end up in like policy and not
That's cute.
like academia, but I just like enjoy studying. And, yeah,
Oh my
I think
goodness,
for
we did
like
that too.
policy careers, like
Wait, no,
there's a pretty high payoff for like doing something like law
That-
school or just getting a terminal
Stop!
degree. Even if you
Wait. Oh my god, wait.
there's a yeah, I'm like kind of thinking
You
that.
gotta have one.
I guess like we'll see like
Are you
what policy and the opportunities that are. Are you thinking grad school?
Is it? Oh, wait.
Okay.
You did financial.
but now I'm thinking I'm gonna
Oh, okay. Then I don't know. Okay. I'm Mexican, so I speak Spanish, like Mexican Spanish.
it's very easy to feel the hype about doing journalism.
Yeah.
So that's where I'm at the moment.
Nice.
No, I get super nervous. I mean,
I'm probably gonna
I think it's good, like,
but
but definitely like when there's an opportunity to actually like okay, I'm like
so I'm like
pooping myself.
very
And I'm like I stutter. Yeah. But I stutter and I'm like,
It's sort of like June 4th or 5th or something like that. The time you guys did, I just don't really come to these. I feel like go for I mean before anyway, so
Me too. I was gonna say
but I went to come say
I feel like learning languages it's like so beautiful like being able to speak so many. Like people who can speak like I'm like, well like that's crazy. It's like when's the time? What's the time?
That used to be my goal, was like to be able to speak
I have one that's numbers. Numbers.
Really just
Wait, are you gonna do like? Okay, and then just not. Oh, I guess.
Look at these shoes.
So for that thesis, do you have to like submit your thesis somewhere? Okay, so that's not for like it's not like the grad school deadline application. It's just
I know that like as long as you just have to defend your thesis, but you're gonna do it. Like that's the only like hard deadline. How does he know you can't graduate first?
I've got a UC San Diego. Say that right now. I just took a look again. I was just kidding.
She kept saying last night. She was like,
I took a look again. I'm just kidding. I'm
I'm
back.
glad I applied to Berkeley. I'm glad I ended up not.
I just like girl. Last night.
I think a lot of people like the idea of but just for my school, I've heard a lot about like they're just like not diverse and stuff like that.
That's kind of what I've heard since like
You just know.
meeting more people in college.
Yeah,
No, I mean, like,
that's a good question.
wearing your glasses if you're prescribed glasses. Oh, God.
You know, they claim.
No, I thought you meant like
We're not.
Same with Boulder. No, like this the wet. Yeah.
And then you have like I've done a picture, and it's like the one group on campus.
parked cars, and then I try to park, and there's like so much room in the parking lot. I'm just so bad at parking. I just hit another parked car. In the car.
Like just
The insurance increase. Me too. I think you should introduce him as Dr. Big Mac. Please, Dr. Big Mac.
Dang it.
What's he a doctor of? I was just thinking fishing. Oh my god. Wow. We're gonna give the least serious thriller. Did they put that up on YouTube? They've gotta. What is a biogen? I guess we'll find out. I guess we'll find out. Oh my god. The anticipation's key.
Hello. I think we're going to go ahead and get started. So my name is Sierra Janae. I'm a rising senior at the University of Colorado Boulder. This summer I'm working here as an astronomy REU student, and I'm working with Helen Wang on Martian meteorology.
Hi, everyone. My name is Bridget Vasquez Segovia. I am also an astro intern, currently working with Priyanka Chakraborty and Adam Foster on active galactic nuclei. And we are very pleased to introduce our speaker for today, Dr. Matthew Ashby.
Uh-oh.
Okay, so Dr. Ashby obtained his bachelor's from the University of Colorado Boulder and his PhD from Cornell University in 1995 and worked under his advisor, Jim Hawk, who was heavily involved in the infrared astronomical satellite mission and the infrared spectrograph on Spitzer. The exposure to these projects is one of the main reasons for why Dr. Ashby feels so connected to the infrared astronomy. From a very young age, Dr. Ashby knew that he loved the idea of doing research. As a result, he decided to pursue research throughout his career. He began working for NASA through the Voyager 2 mission, then worked on a job for LIGO, and worked on a prototype of the Infrared Space Telescope, all before finding himself working here at the CFA.
Oh, okay. Some of his initial work at the CFA was on the NASA submillimeter wave astronomy satellite studying the composition of elements in space. Spitzer then launched, and he worked on that mission for about 20 years as a member of the infrared array camera team. After some time, the SPHEREx project was approved and has become one of Dr. Ashby's main focus areas. Other projects Dr. Ashby is currently involved with include Euclid and the Spitzer Resurrector. Recently, Dr. Ashby received a promotion to the OIR division chair. Dr. Ashby also currently works as one of the directors for the Astro REU. He initially became involved after he was invited to advise an REU student and found out that he really enjoyed the advising process. He started advising more regularly and eventually took over the program after he was invited to become a director. One of the rewards that he didn't anticipate was how much he learned from the students throughout the program. Outside of research, he also enjoys catch and release fishing, woodworking, chess, basketball, and supports an organization in Concord called Dignity and Asylum. Dr. Ashby said he has thoroughly enjoyed his time here at the CFA and loves working along people with so many different areas of expertise. So please join me again in welcoming Dr. Matthew Ashby.
Thank you for that very kind introduction. I really appreciate it. And I'm very grateful for that. I am going to talk about SPHEREx, but in a strange kind of boomerang situation. I am now going to tell you about my path in the sciences, a lot of which you've just heard. So I'll be able to get through this fairly quickly. Some of it may be new to some of you, though, I hope. I started at CU Boulder, as you know. I was actually kind of on the fence. I really liked physics, but I also really liked English. I liked the art of it. I liked literature. I liked the expression. So I was actually an English major. And my heart swelled with pride when I got my first job as an English major, as a sophomore, only to be crushed the next day when my supervisor just fired me only because someone she liked better walked into her office. That was a bitter pill. And I thought, that is so arbitrary. That is just not fair. So I am going to quit. And I got a job, I'm proud to say, in physics. Well, I didn't get a job. I changed my major to physics the next day. So I'm pretty happy with that decision, as you might infer. Then, as you heard, I got an internship on the Voyager 2 project that fall. So I felt validated with my decision. And this was my introduction to the way NASA does things. And I am really grateful for that internship. That's why I wear this button, pin, whatever. I joined the mission just as they were starting the very outermost tour of the gas giants. Let me try to explain this succinctly. Too bad for you, you have to listen to all this, and I have a moral at the end, so even worse for you. it's Alyssa Goodman's moral, but anyway, I'm going to claim it for today. So my job was to monitor the signal from Voyager 2 as it swept behind Uranus. And what I mean by the NASA way of doing things is, big collaboration, you're part of a team, you're doing something bigger than yourself, people are cooperative, and you have a mission. And in this case, the mission was to monitor the signal from the high-gain antenna, which is unmistakable in any picture of Voyager 2 that you've seen. It's the first thing you notice, the big dish. It was broadcasting continuously to the Deep Space Network as it swept behind the planet, which is itself kind of a stupendous feat for humanity, really, if you think about it, to align everything like that. Must be 1 billion miles away. And by monitoring the signal strength, so now I'm actually getting to my job. So by monitoring the signal strength and the timing and looking at the dips and then the diminishment of the signal and when it winked out and when it came back on and its increase and then the dips on the other side of the planet, we got the conformation of the rings, which was controversial at the time, the number of the rings, their spacing, their distance from the planet, their density from the strength of the dips, and the lapse rate of the planet, and its diameter. It's a stupendous amount of information just from the high-gain antenna, which wasn't even a science instrument. So it's like doing a lot with very little. That was so cool. And I was really like hooked on that way of doing things at that time, and I wanted to do more. So then but I did quit, and because I had to get my grades up after that. So I joined LIGO. LIGO had a presence at CU at that time. And my job, it was so fun. I was like in the machine shop and in the electronics shop, and I made a little device to isolate a test mass for an interferometer so that when the ground moved, the test mass held steady so it could be used as something to hold a mirror in an interferometer. And that was so fun. I cut myself like a bazillion times in the machine shop. It was totally unsafe. They would never do that now, but it was really great. And on the strength of that senior thesis, where my advisor fell asleep, by the way, I think it was that thesis that I got into grad school at Cornell. And after I finished my coursework, I was doing the thing you do, you got to find a thesis project that you believe in. And so I do what I strongly advise you students to do. You talk to the older graduate students, smarter graduate students. So I'm sitting in Terry Herter's lab, which I bet looks exactly the same now as it did then. And Dave Shoup, the nicest guy on earth, sitting there next to me, so intense, working on something. So I say, "Hey, Dave, what are you working on?" And he says, "I'm working on dust." And I say, "That's great, Dave." And I'm thinking, that is the stupidest thing I ever heard. It's like, you could do black holes, you could do cosmology, you could do supernovae, dust. I am not going to wow them at parties with dust. So, so then what did I do? I went and Jim Houck agreed to advise me, and then I wrote a PhD describing the IRAS galaxies, which are basically big dust factories. So I look back on this as like my moment of hubris, right? I had no idea what I was doing. I get it now. Like, at least 2/3 of the papers I've written have been about dust. And I think back on that moment as like, to keep me like grounded. That's super important. So then, I did manage to graduate. And then I came here, I joined SWAS. We did a search for water vapor in the Milky Way. There's water everywhere, water vapor. It's just like, it's so thermodynamically favorable to make water, 2 hydrogens and an oxygen, abundant atoms. So this, SWAS is it's still up there. So a radio observatory in low Earth orbit. You just could not point it anywhere that was forming stars and not find water. It's incredibly successful. And as that was winding down, I got picked up by IRAC, as you heard, did all kinds of things. A lot of dust there. And then towards the end of that mission, I joined SPHEREx, but this was the SMEX version of SPHEREx. And we worked very hard on this proposal, and only to be, we actually got to phase A, did a phase A study for 1 year, 11 months, only to be denied. That was very emotionally challenging. But probably a good thing, because I'm going to be telling you about this version in a little bit. The truth is, it's a good, NASA was right to deny us this version, because the cost cap is only $280 million, and you just can't shoehorn, the tech is not at a point where you can shoehorn this mission into that cost cap. So this is better. I joined Euclid as one of three, as a member of one of 3 US science teams. We're going to kind of, you may have heard that this launched earlier this month successfully. It's on its way to L2. And our role in this is going to be to look for the ghostly light between the galaxies in the northern galactic cap of 14,000 square degrees. That's what we're going to do. I'm going to talk about this a lot. And then we have gotten started with Spitzer Resurrector. And I'll just briefly say what this is. So Spitzer is kind of off. It's in safe mode, I think. It's 2 AU from us linearly. It's on the other side of the sun. If you're looking at the direction of the sun, that's where Spitzer is. We can't use it, even if we had funding. It was turned off for reasons of funding. We can't use it, though, now, because to downlink the data, we'd have to point the high-gain antenna right at the sun. It would burn up. So what we're going to do is we're going to build a tiny little, basically, radio relay. We're going to drop it into a lower orbit, which, of course, as you know, will speed it up, and it's going to go catch Spitzer on the other side of the sun and wake it up. And then we're going to operate it here. This will be we'll have the Science Center here for 2 years as the nominal mission. That's assuming the Space Force lets us do that. I have to tell you, I'm very fond of the NASA way of doing things. The Space Force has a totally different way of doing things. So I don't know how this will pan out. So you might be forgiven if you're looking at this for thinking that I have always been about science, doing my science, and indeed I thought that for the longest time. But as you heard, I did have a student, Paul Sell, in the early 2000s. He was a great REU student. I took him to Kitt Peak. We had an observing run. He looked at dust in nearby starburst galaxies. And then he went and got his PhD in Europe, and now he's a faculty member in Florida. And I thought, man, I learned a lot from Paul. And Paul kind of learned, I think Paul learned a lot from me. And so that really changed my attitude about what I had to offer students. And so when I was invited to become co-director by Jonathan, thank you, Jonathan, of the REU, I said yes. And my life has been so enriched by all these people. And their advisors that I have come to know over the years. And through these people, there's Osase, I have come to know people not just here, not just the students at this institute who come through in the summer, or their advisors who are here in all the divisions, but also the students who go on to get their PhDs, and some are now coming back as postdocs this fall. It's amazing. It's really enriched my life in ways I didn't expect. So I recommend that highly to you students. Okay, so that's a long wind-up, and I'm sorry for that. Thank you for your patience. Now you have to listen to the moral, because it's too early for you to walk out or you'll be thought rude. So the moral is Alyssa Goodman's moral. Embrace your mistakes. I thought I was going to be a better fit for English. Well, that was not true. I thought dust was dumb. That was not true. I thought I didn't have a lot to offer students, or vice versa. That was totally not true. I thought this version of SPHEREx was going to go. Big mistake. So the key, kind of your job, Alyssa Goodman would say, embrace your mistakes. Your mistakes allow you to find the right path, to find the good path. So that's what you should, that's kind of your job as scientists, I think. Just don't make the same mistakes twice or 3 times or 4 times. So try to, productive mistakes is what you want. Like one time, okay, now I did that. I'm not going to go make fun of Dave Shoup again. Actually, I only made fun of him in my head. I know that much. I didn't say it out loud. Okay. So thank you for bearing with me for my moralistic talk. So now's the main event. SPHEREx. We are in phase C. We're going to launch in less than 2 years, unless something bad happens, like another COVID or something. And the takeaway is, so the shtick for SPHEREx is it's all sky. It's an infrared spectroscopic survey. So we're going to paint the entire sky with spectra out to 5 microns. So the whole sky, everything, Milky Way, galaxies, and the spaces between. And that's never been done before. Okay, so these are the people who are making it. JPL and Caltech are the leaders. You can see their roles there. There's a lot of science team members at both those institutions. Ball Aerospace in Boulder, my hometown, is responsible for the telescope and the cover and some of the integration and test, although the telescope has now been delivered to Caltech and is sitting in the basement of Cahill. The science team is all these institutions here. And we have a lot of involvement from KASI, the Korean Astronomy and Space Institute, the Korean equivalent of NASA. And one of the things they've done is make and deliver a very medium-sized thermal vac chamber that we're now doing testing in. And a lot of their scientists are on the ISIS team that I'm going to tell you about. And this is the science team. During our last face-to-face meeting in February, you'll see quite a few CFA people on this list. Joe, who's sitting there in the back, myself, Karen Oberg, Volker Tolles, Gary Melnick. The PI is Jamie Bach, right here in the center, and the project scientist is Olivier Doré. And then there are 3 science themes that drove the design of this mission. And those science themes are led by these people, Gary, Olivier, and Asantha Kure. Perhaps you've heard of Asantha at UC Irvine. And I'm going to talk a lot about those science themes. Oh, but I want to make a point with my first prop. This is important because we scientists, we often think we're so important, okay? So I didn't have a slide for this. So sorry, online people. This is the first light image from Spitzer, which was taken 20 years ago, next month, if you can believe that. And up here, how am I going to do this? So this is the first light image. That's not what's important. Here in this list, and a few people over here, those are the scientists. Okay. Everybody else are the engineers. Almost everybody. Judy Pfeiffer's over here, Craig McGrate, a few people. The proportion of engineers to scientists is pretty high. So my point is, you cannot get these things into space without a lot of engineering support. So look at this science team, right? There's actually a few engineers and managers in there. It's probably 2/3 actual scientists, but they represent a very large, standing army of people. So I just wanted to make that point before I go on. And so here's the main hardware shot. Where am I going to start? Okay, I'm going to start with the spacecraft. So the telescope itself is tiny. It's just 20 centimeters. It's like the size of those tuffets that we sit in the Perkin lobby, right? It's really small. But it has a huge étendue. The field of view is immense, and so we can tile the sky very efficiently with it. It is shielded thermally by the deployed solar panel. So we launched deployed, because we're in a Falcon 9. I mean, there's like an immense space in there. There's so much, I mean, you look at the fairing, it's like a school bus. You could put a school bus in there practically, and we're, down there in a corner. So we can deploy the solar panels, and that way we don't have a thing that's got to snap open and possibly break and not work after launch. Star trackers, this is the spacecraft down here. The spacecraft, and you can sort of see the high gain antenna that will communicate with the near-Earth network in Alaska and Svalbard, and some of the electronics boxes. The spacecraft is warm-ish because it's receiving light from the Earth, but we have this V-groove technology to keep the telescope cold. So the telescope is isolated from the spacecraft by these blunted and progressively tapered solid anodized aluminum cones. And the way this works is photons coming from the spacecraft, which is warm, so it's radiating thermally up in this direction. If you just have plain parallel barriers, the photons can go back and forth. It's not as efficient as this technology, which is, since the openings are tapered to deep space, the photons can rattle out, and that cools very efficiently. So we have no coolant to run out of. So we have a 2-year nominal mission, but we could go for a very long time if NASA sees fit to fund us. That's point number one. Anything more I want to say about that? The telescope is machined from a solid block of aluminum. It's already gone through a little bit of thermal cycling at Caltech. And this is what one of the two focal plane, well, these are the arrays. What do I call the blocks of arrays? I don't know. I'm going to call them blocks of arrays. I could tell, by the way, that we had an experienced science team when this image was first shown to them on the Zoom call, because the ones that weren't muted went, "Oh, it's so black," like that, because the housing is really black. So, they weren't distracted by this. But what you don't want is stray light hitting shiny surfaces and rattling around and getting on your detector in places you don't want. So the fact that this is all anodized so effectively black is great. Anyway, these are our 3 2048 pixel squared arrays for the shortwave focal plane setup. And we have bonded to them these linear variable filters. So this is the thing that took me a while to really understand about SPHEREx. These are, the planetary community has been using these for a very long time. This is the first astrophysics mission I'm aware of that's using them. This is set up so that they pass a wavelength of light as a function of a ray column, as a function of height, as I'm indicating it on the screen. So row, I should have said row, I'm sorry. So row 2048 of this detector is going to see 1.1 microns, and row 1 is going to see 7.5 microns. So SPHEREx does not downlink spectra, and it doesn't downlink images. It downlinks this weird thing, or 6 of them at a go, actually, because this is half of the setup, these spectral images where the wavelength of light gradually changes from top to bottom of each of these images, and then we have to back it out. We have to back out the spectrum of every source in software. So that's the challenge. There's a big challenge for the software. That's very hard for me. It was very hard for me to understand that at first. And so here's a plot of our sensitivity. I guess the point of this plot, so this is 5 sigma AB, point source sensitivity. If you just pay attention to the green bands, that's where we are now. I don't really like this plot, but it's supposed to show that these bands are narrower than our old bands, so we're doing better than we thought we were. So in band 1, which is this detector, band 2 is this detector. This is our sensitivity. It's about the same as Sloan Sky Survey. And here, here we're maybe 3 magnitudes deeper than 2 mass, and out here we're comparable to All-Wise. But what we're going to do is use these LVFs to break up every one of the spectral images into channels. So we'll have 102 channels in software for every target we look. So the trick is you have to get every point of the sky observed with every part, or at least every row, of every one of these detectors during the mission. If that makes sense. That was very hard for me to grasp at first. So that's what this looks like here. This is our band 5 array, illuminated with a monochromator where we're varying the wavelengths. And so it's only passing light to certain parts of the array depending on the wavelength being emitted. And we've arbitrarily decided, well, actually it's not arbitrary at all. What am I saying? We very carefully chose to break the light up into 17 channels here. So we have 102 in total. And these are the band passes for what you're seeing in this animation here. There's a little bit of curvature in it because it's very hard to make these LVFs, perfectly straight. It's just a manufacturing tolerance thing. By the way, here's the Kazi chamber. That's Howard, one of the chief engineers. That's Christine, one of the software engineers, who's been dragooned into helping with an engineering effort. We actually measured the filter bandpass for every pixel of every one of our 6 detectors, and so some people who couldn't escape got pulled into that effort. So we have 2 engineers and 3 software people who had to help with that day. So this is what the arrays look like. This is what they look like when they're bonded with the LVFs. And this is our bandpass in one of our 6 arrays. So we already have all our arrays. We have our filters. We have our telescope. It's all getting tested in this chamber right now. We don't have all the parts. We don't have some of the spacecraft parts. I don't think we have the star trackers. We don't have the solar panels. But we have a lot, and it's getting built right now. So, but what this means is we don't have parts that can break on orbit. So how we accumulate spectra is just by nodding the telescope. So we get up into orbit, we nod the telescope, and we just take a succession of rastered exposures, and sources are seen to move across the detector that way. And in this, so this graphic on the bottom is showing you how we accumulate a spectrum. We do it by taking 51 exposures, so we get 2 spectral points per exposure on each side of the dichroic. And in 6 months, as we do the whole sky, we'll get this entire thing for everything on the sky. And the team at Arizona has actually managed to figure out every exposure for the 2 months, 25 months of the mission already. So here's the field of regard, avoiding the sun. These trapezoids are temporal segments in the low Earth orbit. SPHEREx is here in this visualization. And what you can see are the successive exposures being taken as we build up spectral coverage in the field of regard. Now the spacecraft is orbiting, so it's moving ahead of the field of regard, and so occasionally it has to snap forward and build up coverage of a different patch of sky. So in this 98-minute low Earth orbit, it's building up patchy coverage in a great circle, but there's 18 of those in a day. So in a day, it can build up kind of a rough-looking great circle that's mostly complete, but not fully complete. I hope that's visible with the light there. Here you can see everything deployed, the solar panels, the high-gain antenna, the star trackers, the photon shields and everything. And what this looks like over the course of a year, or actually just 6 months, is this is vastly accelerated for pedagogical purposes. This is the coverage map here, okay? The folks at Arizona State really have kind of miraculously figured out how to cover the sky so amazingly evenly. You can think about it as a geometry problem, which I guess it really is, but I guess you can't see. I don't know could we dim the lights just temporarily? This is their this is the depth of coverage map, and it's basically flat. The thing that it doesn't show is that we're actually stealing exposures from every one of those orbits, many exposures, to build up coverage at the north and south ecliptic poles, because we're doing science, different science there that I'm going to talk about. Okay. All right. Oh, and I'm going to talk about it now. All right. So any questions about any of that before I go on? Yes.
I might have missed this, but what's the wavelength range of each of the rows? Is it one wavelength or does it capture?
Yes, thank you for that question. It varies depending on the detector, because at long wavelengths we want narrow, we want relatively fine wavelength coverage. So the resolution, the resolving power is a little bit over 100. But at shorter wavelengths, we don't need that much resolving power, so we can use a coarser approach and more efficient gathering of photons in higher signal to noise. So overall, it varies from like 45 to 130. Yes.
Are there plans for like doing repeated surveys?
Yes. Great question. So that video I just showed you, we're going to do that 4 times in the nominal mission. So every 6 months, we'll cover the entire sky, plus the ecliptic poles deeply. So if there's like a quasar that's varying, for example, or a young stellar object, the redder they are, the more they vary, we will get that spectrally, which will be pretty cool. Yes. And of course, the more epochs you get, the better your ability to resolve that spectral variability. Yes, and you had a question.
It was essentially the same question.
Okay. All right. Yes.
What time that it takes to build up a single spectrum for an object during the nodding procedure? Is it like 5 minutes, 10 minutes?
That is such an insightful question because we have been wrestling with that very problem. You would think that it would only take a few orbits, but it turns out because of the moon avoidance, the sun avoidance, the fact that we're following the terminator and we're stealing observations from every orbit to populate the ecliptic poles, it's actually quite a complex function of time how we fill in the spectral coverage for any one object. And for a given object, it can actually take as much as 18 days or even longer, depending on the ecliptic latitude.
But do you worry about time variability in the spectrum then?
We totally do. Yes. So it's a big problem. So I'm going to put a pin in that. And when I get to the water ices, please raise your hand again. Okay. All right. So now I'm going to talk about the sphere. All right. I need to move on before anybody embarrasses me with other such questions. So when you're selling a mission to NASA, often what you do is you focus on 3 main science questions, and that you document them very well. You assert that you can answer them very thoroughly, but in a general purpose observatory such as an IR all-sky survey, there's many uses to which these data can be put. But these are the questions we used to sell this mission to NASA. There's a cosmology one, there's a galaxy evolution one, and then there's the one that those of us here at the CFA are involved in, which is doing an assay, a chemical assay of the Milky Way and the Magellanic Clouds for water ices and other precursors of biology. So I apologize for showing you this thing again. I'm sure you've seen it a million times. And the point of this is in the trillionth of a trillionth of a trillionth of a trillionth of a millionth of a second that was cosmic inflation, we don't really know what happened, what drove it, what made the universe expand catastrophically into this. So SPHEREx is going to get at that question. The tool that we want, well, one of many tools that are available to tackle that is the map of the cosmic microwave background from 300,000 years after the Big Bang, because inflation should have frozen out, depending on how inflation progressed, that information should be frozen out in this map and should be reflected in deviations from Gaussianity in this map. The issue is that it's kind of coarse and it's only two-dimensional. All right, so this is a little graphic saying non-Gaussianity, okay? So that's what people look for, and the constraints are two-dimensional if you're relying on the CMB. What SPHEREx is going to do is detect about 450 million galaxies with sufficient signal to noise to measure 10% redshifts, and about 10 to the 7 of them with extremely precise redshifts. We're going to use template fitting to do this. And this is just an illustration of how that's going to progress. Faint galaxies, we have relatively faint spectrophotometry. For bright galaxies, we have really good spectrophotometry, so that governs how well we can constrain the redshifts. That's what that's illustrating. But the point is, we can get lots of galaxies in 3 dimensions, and so we can construct models of how are galaxy pairs distributed and how are galaxy triples distributed in space, the spectrum and the bispectrum, and those are reflective of the models under which inflation, those are not the models, but those are reflective of how inflation progressed. I think I finally said it right. The current constraint, I think it's FNL, that's the so-called non-Gaussianity parameter. I think this expression of FNL being about 5 is thought to be pessimistic now. It's thought to be more like 3. John, you probably know better. But of order 3, right? And so in these extreme illustrations, if you have non-Gaussianity of 1,000, you get much more pronounced voids and condensations of the underlying dark matter. If you get something closer to 0, this is what the distribution looks like of dark matter. And so the bispectrum and the power spectrum are diagnostic of that. And there's literally models, like lists of models of that describe inflation like as long as both my arms. So in this plot here, this is an indicative plot out of date now that indicates here a 1 sigma, 68% confidence contour of where the running of the spectral index would be based on prior measurements. And we think that with the SPHEREx power spectrum and bispectrum measurements combined, we can do a very powerful job and get of order 1, of order unity constraint on this. And so we think, we don't believe that we're going to isolate the model, okay? But we do think that we'll be able to isolate classes of models depending on where this is localized in this space. Whether there's multi-field inflation or single-field inflation, we think we can get a handle on that. So that's the job. That's one of the main science themes of SPHEREx. Science theme 2, and I'm not involved in this on the SPHEREx team, but I am involved in this on the Euclid science team. Let me try to describe this. If you take an image and you regard it as an onion, and you mask out, it's like peeling away layers, you mask out the bright sources, and you do that iteratively on progressively fainter sources. It's like taking away layers of an onion until there's no sources left. All you have are the so-called source-free pixels in your image. It's not truly blank, though. What you have is a statistical expression of the light, of the faint light, from all the sources that are just below your detection threshold. Okay? And the team led by Sasha Kashlinsky at NASA Goddard in 2005 published these so-called fluctuations, that are an expression of the clustering and the colors of the fluctuation. So if you do it in multiple you do this exercise in multiple bands, you can get the colors of the undetected sources. And you can also measure their power spectrum, so you can get their clustering behavior. So there's a spatial part and a spectral part, and that's diagnostic of what the sources are. We don't know what they are. We wasted a lot of time actually fighting over, was this signal even real, for several years. It is totally real. So with SPHEREx, we're going to do this in the north and south ecliptic poles, not over just 8 arc minutes, but over 100 square degrees. And this is an illustration of why that's useful. I mean, usually what people often do, you can do the approach I just described. You use the galaxies, you measure their redshift, you have their positions, you know where they are. They're like 3D test masses. So that's how you're measuring what's going on out there in the universe. That's one way to do it. But if you remove those and then look at the underlying signal, that's all this faint stuff that's hidden. It's like, what I was referring to as ghost light before. And that's what we're going to look at with SPHEREx. And we can figure out in the aggregate what is causing this signal. And these are some of the candidates, not all of them. Are they the faint arms of galaxies, faint tidal tails of merging galaxies in the nearby universe? That is a popular explanation. Are they primordial galaxies? Are they primordial AGN? Quite a bit of controversy over that. There's sort of like I said, there's two handles that you can use to get at this. There's the spatial and the spectral. So here's one step forward that was made recently. Chandra spent 23 days staring at the Hubble Deep Field, and this was that image. All these things are active galactic nuclei. Spitzer spent, I don't even know, like 2 weeks, a comparable amount of time staring at the same field. And at this stretch, you can't even see all the tens of thousands of sources there were in there. I worked very hard to make that mosaic, believe me. And this is what you call source confused. It's not like the X-ray image. There's so many sources in here, they're actually overlapping, they're on top of each other. It's very difficult to get them out. But this was done by an incredibly brilliant postdoc at Goddard. And what she found when she had done that in the X-ray image and both the 3.6 and 4.5 micron image was that the fluctuations were correlated. And this was a big surprise. Why should this be? Why should the infrared and the X-ray non-sources be correlated? It means that the faint stuff that you can't detect is the same stuff. And so it's not correlated at the strong, the hard X-rays are not correlated, but both the soft X-rays are at both infrared bands. These are totally independent mosaics that I made. So why is that? We don't know. Are they primordial stars, high redshift AGNs, or X-ray binaries, that are at medium redshifts. So SPHEREx will iron that out. Here's an illustration of how it will do that. Here are some signals measured by Spitzer, a Japanese mission called Akari Cyber. These are actual measurements. And this is a model of galaxies seen at the epoch of reionization. Of course, they have a Lyman break here. And so we're going to bin up the signal in these ecliptic pole fields, not 102 channels, but like 9. And then things seen at the epoch of reionization will drop out here. And so we can combine all these measurements to discriminate the nearby stuff from the distant stuff. That's the shtick there. Okay, so now I'm going to talk about what I supposedly know about instead of what other people know about. The search for prebiotic molecules outside the solar system in the Milky Way. So the idea here is very simple. We're going to look at background stars as seen along lines of sight that intercept foreground clouds of various kinds. Dense clouds, young stellar envelopes, protoplanetary disks, and young stellar systems. And by seeing the light in absorption, we can, and this is an example from ISO up here, we can figure out what they're made of, what the intervening clouds are made of. So there's quite a rich variety of molecules that are detected in this spectral range, particularly water. Just like SWAS was seeing in water vapor, though, this is seeing ice, water ice. And water ice is like literally 1,000 times more abundant than water vapor. And you can see it, well, actually, oh yeah, right. So, sorry. So these are the people involved in the team. Gary Melnick is the lead. There's quite a few people here at the CFA involved, and also a lot of people at CASI. Jung-Eun Lee is a professor at Seoul National University who has herself trained, I would say, probably the majority of experts in ICES and YSO variability in Korea. And many of these people are her students and postdocs. Do I want to say more about that? No. Okay. So this is the team. And if I were to give you like the elevator pitch question of what are we doing with this science theme, it is we're trying to figure out where did the water on Earth come from? Did the water form in situ out of the solar neighbor, out of the solar nebula? Or did it form out in the Oort cloud or the Kuiper belt and rain down from there, somewhere else? That's the question. And here's a couple references that are very authoritatively describing the state of knowledge of the field. Here are 6 spectra from Edith Gibbs' paper. It was a spectral atlas paper, ISO, SWS spectra, showing the variety that these objects can present. But always the water feature is so strong. It's like, this is a honking strong feature. We are not going to miss it with SPHEREx. But then these other features are present in a tremendous variety. So our challenge on the ISIS team will be to somehow manage to analyze sources like this reliably. That's what we're engaged in right now. Here's an example of a case study done by Webb recently. So if this is chameleon, this is a molecular cloud in chameleon. If in this box, this is the Herschel, I've forgotten what band, 550 micron, I don't know, map of that in that box. And these 2 yellow icons mark the positions of some stars that are behind this incredibly dense condensation in this cloud. All right, and this is kind of mind-blowing. I want you to appreciate James Webb power here. So first off, allow me to point out that the optical extinction through which these things are seen are 95 visual magnitudes and 60 visual magnitudes. Think about that for a minute. That's why we don't have, any information out here shortward of 3.5 microns, because it just wouldn't make it at all. But every single one of these colored features is believed to be, colored segments, is believed to represent a detection of a molecule from behind that incredibly dense foreground screen. And of course, here's water. Water stretch. Here's water again. But there's all this other stuff, methanol, ammonia, methane, just this incredible, rich chemistry happening in those clouds as illuminated by the background stars. And this same team, Melissa McClure's team, I am aware because Joe and I have friends on the team, are about to publish more spectra like this that show similar mind-boggling chemistry. So we're going to chase things like this with SPHEREx, although of course our spectra will only come up to 5 microns, and we will not have the resolving power to see this kind of stupendous structure, because we have only a resolving power of 130. But we will detect these features, look how strong they are, and we'll detect water and some of these other things very well. And we will have be able to include the shorter wavelength channels that will allow us to model those clouds very accurately. And so we have selected targets. This looks like an image, but it's not. It's just a collection of dots where we have put all, oh, Andrew, I can finally answer your question. So the problem is with the variability. If you have variability, you're going to blur these features because the spectra will move up and down over time. So if your background source is varying, or you're looking at a protoplanetary disk or a really red YSO, your ability to discern a reliable measurement of these absorption features is badly compromised. That's in a nutshell. And some fraction, we know some fraction of them will be variable, and we've already built metrics into our prototype pipeline to detect that variability on the continuum so we can be aware of it. Glad I remembered that point. That's super important. Okay, so this is 8.6 million dots where the color represents what we think is the likely, oh, thank you, the likely foreground dust screen. That on the wall is the updated version of it with 9 million sources. And you can see this filamentary structure. By the way, this is row OF. If you were paying attention to the web announcement yesterday, that's where it is, right there. But I'm just going to zoom in on this region right here in Cygnus to give you an idea of how this looks. This is the filamentary structure, the condensations of gas and dust as traced by WISE at 3 microns, and all our sources locate there. Pretty much, that's 25,000 discrete sources that are bright enough, isolated enough, and red enough to be well detected and yield ice spectra for SPHEREx. So that's what we're going to do. And we're going to use this catalog with this tremendous statistical power, millions of sources, to tell a story about how how the chemical content evolves in the lifetime of systems like this. That's what we're doing. That's pretty cool. I'm pretty jazzed by that. So I've told you about the 3 main science themes, but it's an all-sky catalog. It's an all-sky survey. We're going to see everything. Everything will be in the public domain. And you young people, you can go mine this archive. And you can combine it with Rubin, with Roman, with Webb, with everything that's going on, get the spectral domain to the imaging domain, or look at it in detail with Webb, what you see coarsely with SPHEREx. It's going to be incredible. And you'll see all these things. Okay? So pay attention to that. All right. And this is my last slide. So what are we? SPHEREx. We're, well, yes, we are on track for launch in a little less than 2 years. These are the 3 science themes that I've described to you. A lot of hardware is in the basement of Cahill Physics at Caltech right now being integrated and tested. We've had several thermal vac cycles on progressively more complicated assemblies of that. And we are progressing towards launch. So thank you for your attention, and I'm happy to take questions.
Thank you so much for that talk. We really, really loved it. Inspirational. Okay, now it's time for some questions. We understand that it's 5 if some people have to go, but we will definitely be taking questions. Yes.
Hi. So in the densest regions of the galactic plane where you have most of your targets, is the 6 arcsecond pixel, is that a problem?
Yes, it is a problem. So obviously as you progress towards the midplane and towards the galactic center, source confusion sets in. Nonetheless, we can identify spatially isolated sources that we can get spectra for that are not spectrally contaminated. So it's a little bit of a trick. So a lot of our effort actually has gone into developing the catalog of those sources. It's non-trivial, but yes, it's doable.
So when you showed those 25,000 sources, are those 25,000 isolated sources? Or?
Yes.
Okay.
Yeah, they're all spatially isolated. They're bright. They're red, indicative of dust foreground. So one thing I haven't shared with you is that AGB stars are spread throughout the Milky Way. We'll see them all the way through the midplane to the other side of the galaxy, and in the Magellanic clouds, many AGB stars. So they will be a significant contaminant, or a contaminant, but we'll know as soon as we get the spectrum that we've got one. So that'll be an issue for us. But if someone wanted to do a PhD thesis on AGB variability, we'll have at least 4 epochs of all of them in the Milky Way. That would be pretty great.
Yes, Anya.
This is about variable spectra again. How do you foresee being able to use a spectrum that is flagged as variable to like do science apart from just saying this spectrum is kind of blurry, so and we know that it's the variable source, if that makes sense?
We're not, so I didn't mean to overstate, we're not confident that we can actually do absorption feature spectroscopy or science with variable sources at the moment. Now, so we have metrics that we can use to measure the variability. In fact, we have maybe 4 or 5 that we've developed. And one of the things that our Korean colleagues are experts at, Jung-Eun Lee in particular, is YSO variability and measuring it. So there's a threshold. If you stay below the threshold, then we can work. But if you exceed the threshold, you might have to throw those sources out. But since we've got 9 million, we might even be grateful to throw some sources out, to be honest.
I think I saw Ramisa's hand first.
So I know that you mentioned you're gonna do like 4 repeated surveys. When exactly can SPHEREx do like targeted, like focus on like a specific target and do observations of that? Or?
Well, right. So it is going to do the whole sky. So any specific target will just by default get observed 4 times, unless it's within maybe 12 degrees 13, 14, 15 degrees of the north or south ecliptic pole. Then it will be observed thousands of times. So in fact, one of our tricks is we're calibrating using stars at the poles because we'll get so much more photometric information from those. Now, if we have an extended mission, then we'll get even more. But even at a MIDEX budget, it's too heavy of a lift to do like a geo-observing program. It's just too hard. So we'll have some observer support, but basically that means archival research. Yeah.
Yes, Jonathan.
For the extragalactic side, you're going to be getting data on a whole large number of galaxies, which is not incredibly different in some ways from the science that Euclid and Roman are going to be looking at. So I'm wondering what complementarity there is between the extragalactic SPHEREx data and the galaxy surveys that Euclid and Roman are going to do.
Right, so Euclid has a far superior point spread function to us, and so it will know what's what. In fact, in a certain sense, we have some plans to use what they're doing to back out source multiplicity. Roman will be even better by another factor of 2. And hopefully Roman will be used to do, I would be so thrilled if Roman were used to do an all-sky survey. But the main difference is in wavelength coverage, because SPHEREx goes over several octaves from 0.75 to 5 microns. And so for nearby galaxies, you get a good estimate of the stellar mass and the emission lines. And then for more distant ones, you can get the Lyman break. So I don't think you're going to get the same spectral coverage from Euclid. You know, Euclid does have a spectroscopic capability.
I think I saw one hand somewhere here. I think you were first. Yeah, you can. Sorry.
I just wondering, because you mentioned the intra-halo light, and I just wondering how deep the final data will be, and for each orbit of each node to target how deep it is.
Right. It's an important question. So the question is, how deep will the fields at the north and south ecliptic poles be? Because the depth will limit what you can say about the sources that are there and whether you can actually measure the intrahalo light. So this diagram shows our sensitivity over the whole sky. And we should be about 1.5 magnitudes deeper in the north and south ecliptic poles. So quite a bit deeper, factors of 5-ish. It's partially a function of sensitivity, so we have that, and partially a function of angle, because that the things that are clustering, you can measure the angular correlation function as a function of band, and that will also be diagnostic. Yeah.
Okay, so perhaps one more question? Yes.
Yeah, so I'm wondering if I'm missing something biogenic. ICE is not being my field, but so when it comes to cosmology and counting galaxies by spectrum and all that, I understand those are very statistical subjects. If you want full sky coverage, that makes sense to me. But when it comes to understanding ice on Earth, where it came from, I don't understand why that's a statistical question, and why an all-sky spectroscopic survey is needed, and why, detailed study of a few protoplanetary systems, that's not, why aren't the answers coming from there?
That's kind of a profound question. I think the reason is that sources such as the one in Chameleon, like Melissa McClure, the spectrum from Chameleon that I showed, they tend to be idiosyncratic. They all have their own they all have their own properties that are peculiar to them. And so what we hope to do is iron those out by casting a very wide net, and therefore getting an idea of what's happening throughout the Milky Way. Not just one source that, I mean, I could just make something up, like that particular cloud might be descended from two parent clouds that impacted because they were pushed by two particular supernovae and have a particular chemical abundance that's not representative. So we want to sample all these parameter spaces. We want dimensions of the parameter space, the chemical abundance, the UV radiation field, the density, the galactic distance, all those things, so we have a representative sample. Does that answer your question? So we don't think we can do that with a few. Webb will get incredible detail, but it won't be, we hope they don't eat our lunch. We don't think they can get enough to, they probably will get hundreds, but not millions. Yes.
Thank you.
All right, perfect. Thank you so much. Let's give another round of applause for our speaker. And Dr. Ashby will be available for questions right after as well. So if you have some more, come on up.
All right, thank you very much.
Thank you. Thank you for doing this, man.
Sure, that was fun.
I have a harder question. So, not just variability can be a problem, but it's something because you're getting things